It is my greatest pleasure and honor to give an invited talk at this symposium. The title of my talk is A New Transportation Program on a Graph with Sending and Bringing Back Operations. Before giving a talk, I would like to thank Program Committee to invite me as one of the invited speakers. And I would like to thank especially Soki Hong and Subhashchandra Nandi and Ryuhei Uehara, and also Sosanda A, Rector of UIT Myanmar, and all members in the steering committee, the program committee, and the organizing committee. Before giving my talk, I would like to introduce myself briefly. I got a Doctor of Engineering in 1977, and in the year I joined Osaka Electrocommunication University, and I moved in 1997 to JAIST, Japan Advanced Institute of Science and Technology. And I served as a president of JAIST for 6 years. And then last year, I moved to Kanazawa University as an auditor. President's job was not research, of course, but one good thing is that everybody believes that the president must be very busy. But honestly speaking, I had a lot of free time, so I could continue my research in a secret way. Because I just need pencil and paper to do my research, so no one could distinguish whether I'm doing my research or doing my management. And I visited many countries as a president, but the most impressive visit is when I visited UIT Myanmar about a few years ago to give some invited talk at some symposium. During my president, after 6 years, my brain doesn't work well anymore, and so I'm afraid that I made so many mistakes. So I'm afraid that some of my results in this talk may have some bug. And motivation is very important, I think, to start a new research. So let me talk about my motivation first. A few years ago, a president of some Japanese company visited me and talked about his project. His project was not for business, but for promote the status of poor ladies in some developing countries. Suppose there are many places to store many kinds of commodities. If some commodity is needed in a place, commodity is transported from neighboring places. And so they want to hire many ladies to watch the amount of commodities there. And vehicles are needed for those transportations. And so those ladies are encouraged to buy a cheap vehicle for those transportations. But they didn't have good algorithms. So that they asked me to design a good algorithm for finding transportation to meet all needs. That is my motivation. Let me explain my program using a very simple example. In this example, we have 3 places to store many different kinds of commodities. In here, we have melon, kiwi, and grapes. And this mark shows that this node has need of grape, and this node has need of melon and kiwi. And to meet these needs, we use transportation. We use a vehicle available at each node. For example, we use the vehicle here to send grape from this node to this node to meet the need of grape here. And on the way back, using the same vehicle, we send a melon. We bring back melon to here. And then the need of melon is met. At the same time, we use a vehicle here to send kiwi from here to here to meet the need of kiwi here. So in this way, we can meet all the needs. Let me explain using another example. In this example, each place has 3 kinds of commodities. And positive number means that that amount of commodity is stored in this node. And the negative sign means that we need that amount of commodity at this node. And so, but also have a loading capacity of each vehicle. Suppose we want to send some units from here to here, say 80 units from here to here, and 20 units from here to here. And the total is 100 loading capacity. And then the amount of commodity is reduced to 40 and 100 and 0, and the amount of commodity at node G is also changed like this. Here we could transport some units from the second commodity from here to here, but we don't do that because we are only interested in a single round of transportations, so that it is not effective to transfer a positive weight to positive weight. So we never transport a positive weight to positive weight. Only send the positive weight to negative weight, only. Okay, and sometimes we need a bidirectional transportation like this from between G and E. And so in this case, we send 0 units, but we bring back 100 units for the first commodity. And we also send 100 units of commodity for the first one, and then bring back 80 units for the second one. And as a result of this bidirectional transportation, the amount of commodities at node G is changed to like this, and at node E, it's changed to like this. And once we introduce bidirectional transportation, transportation at other nodes are constrained so that they are directed toward this bidirectional edges. This constraint comes from that each node has only one vehicle, so that so let me define a problem more formally. Assume 8 different commodities. The amount of commodities associated with a node U is specified by the vector W1 through WH. And the positive number means that amount of commodities are stored at node U. And the negative sign means that that amount of commodities are needed at node U. And the transportation at node U using a vehicle at node U is given by specifying the original node U and the target node tau U and the amount of commodity to be sent and the amount of commodity to be brought back. And we also have a constraint on the loading capacity. So the total amount of commodity to be sent is at most C, and the total amount of commodities to be brought back is also at most C. Then another notice is that we always transport non-negative quantity of commodity, and we never load more than there exists at a node. And we have another important assumption called order independence assumption. All the vehicles start at the same time, and the transportation must be independent of their order. It is not possible to wait for some load from a neighbor to send them to the other neighbors. Otherwise, we could send some load from a node to a faraway node, but it's time-consuming. And we have a constraint from a single round of transportation. That means we only consider a single round transportation. So no transportation from positive weight to positive weight is considered. So we only consider transportation from a positive weight to negative weight only. And we define our single round transportations as a set of transportation at all nodes. Then we consider two problems, one on feasibility and the other on optimization. And in the feasibility problem, we want to determine whether there is a single round of transportation that meets all needs. And in optimization problem, we want to find a single round transportations that minimize the largest need. There are a lot of related works. Of course, flow network is related to this problem. But in a flow network, a capacity is associated with each edge, and the amount of flow through an edge cannot exceed the capacity of the edge. We can send at every node more than one type of flow through edges incident to the node. But in our program, for each node, we must choose at most one of those edges incident to the node to send and bring commodities back through the edge. Measuring the earth mover's distance is also related to our program. And this problem is defined by a set of piles and a set of holes. And for each pile, we have the amount of soil. And for each hole, we have a size of holes. And earth mover's distance is given by the minimum cost to fill in all the holes using the earth movers. So here is a small example. We have two piles of the size 0.3 and 0.5, and we have three holes of the size of 0.2 and 0.2 and 0.3. And to fill in all the hole, one way is doing like this. And there is another way of filling holes. And comparing the red solution and the blue solution, you will see the red one is better. And the cost of this red one defines the earth mover's distance. So the earth mover's distance problem is very similar to our program, but it is different from our model, because in our program, we consider not only one kind of commodity, but many kinds. And transportations are restricted only between adjacent nodes. and send and bring back operations are possible, and distances and weights of commodities are discarded. And there is a constraint on the loading capacity. So here is an outline of my talk. I will start with a one-dimensional case, and I will give a linear time algorithm for some case and a polynomial time algorithm for another case. And for our general graph, the program is unfortunately NP-complete. So I briefly sketch the proof of NP-completeness of the program. And for our general graph, I will give a polynomial time algorithm for some restricted class of graphs, including forest. Let me start with one-dimensional case. And easy case first, say without capacity constraint, we can load infinitely many loads. Okay? And in this special case, we can show that the greedy algorithm works for a multi-commodity program. And in greedy algorithm is to repeat sending the largest possible amount of commodity to the neighbor and bringing back the largest amount again. So here is a small example. Okay, we have 3 kinds of commodities, and in the first place, we send 130 and 0 and 180 units from node 1 to node 2. Here we need 130 units here. So we just send 130 units from here to here. And then we bring back 210 units to meet this need. And then we proceed to the next one, and the next one, and next one, and next one. And finally, in this case, we see that all the needs are met. Once we know that this greedy algorithm achieve that feasibility, then we can implement all these transportation at the same time. So this algorithm works in linear time. So we have a lemma that given a multi-commodity transportation program on a one-dimensional array, we can determine in linear time whether there is a single round of transportation that meets all needs if there is no constraint on the loading capacity. But what about the case of finite loading capacity? This makes it complicated, okay? And in this example, we assume that the loading capacity is 100. So again, we have 3 kinds of commodities and 4 nodes. And each node has 1 vehicle. And so we can use that vehicle for the transportation. So one way is like this. Node 1 visit node 2, and node 2 visit node 3, and so on. And we have bi-directional transportation between node 3 and 4. And if we specify those transportation by using these parameters, then we can define such a linear inequalities. For example, in here, we send S1, S2, S3 units of commodity from node 1 to node 2. And since the first commodity is negative, so the S1 must be 0. And S2 means S2 is bounded by 30, and S3 is bounded by 50, and so on. And we also have inequalities for the amount of commodity to be brought back. And we also have a constraint on the loading capacity. The total amount of loads is bounded by loading capacity, in this case 100. And the total amount of commodity to be brought back is also bounded by 100. And after implementing this transportation, the amount of commodities for the first commodity becomes minus 40 minus S11 plus B11. And as a result, the amount of commodity must be non-negative, so that we have these inequalities. We also have equality in linear equalities like for here and for here and here. And we have many such linear inequalities. And if there is a solution satisfying all these linear inequalities, then we have a solution, feasible solutions. Otherwise, it is not feasible. But we have different edge directions. For example, we can direct like this. In here, we have bidirectional transportation between node 2 and node 3. And then we have a different set of linear equality, different linear program. And in some case, we may have 2 places for bidirectional transportation like this. So in each vehicle, at each node, 1 vehicle is available, and each vehicle can be directed in 2 different ways. So in total, we have 2 to the n different ways of directing edges. But fortunately, we can solve this problem using dynamic programming, avoiding the exponential search. So key idea is dynamic programming, and this lemma proved that we can solve the problem using dynamic programming. And the proof is as follows. Let G be an input-weighted graph, and GD be a realization of G. And when GD consists of more than one connected component, G is feasible if and only if each component of GD is feasible. This exhibits an optimal substructure. And it is also rather easy to extend the above results to an algorithm for determining the minimum need that we can achieve by a single round of transportations. So, for example, so suppose we know the optimal partition of the one-dimensional array. So in this case, we have a partition of 4 places. And in each connected component, we may have different ways of directing edges. So in this case, we have 3 places for double edges, bidirectional transportation, and also we may not have bidirectional transportation. But we can enumerate all these patterns, and in each pattern corresponds to a linear program. So if we solve all these linear programs, then we have an optimal solution. So here is an algorithm for finding an optimal solution based on dynamic programming. The first step is for preprocessing. For each ij, we assume that the nodes between I and j form one connected component. There is no cut. And then we can enumerate all these patterns. And by solving those linear programs, we can choose the best solution among them. And the best solution, the value of the best solution is set to Tij. So this is pre-processing steps. And in the second step is dynamic programming steps. And so this step is usual dynamic programming. And so we compare Tij and with a case where we have cut between k and k plus 1. So we have a theorem that given an instance of multi-commodity transportation problem, we can determine in polynomial time whether there is a single round of transportation that meets all needs. And we also have a corollary that we can determine polynomial time the minimum need we can achieve by a single round of transportation. So the problem for our general graph is unfortunately NP-complete. The proof is based on the reduction from integer partition problem. Let's A1 through A sub 2n be instance of integer partition, and where the sum of all the elements is 2 times A. And we prepare a set of nodes, say U1 through U2n plus 2. And for each I, W of Ui, or weight of a node of Ui is set to A plus A sub I. And for two special nodes, the weights are defined by 2n squared times A, which is very large. And also we have two special nodes, V1 and V2. And the weight of V1 and V2 are defined by minus 2n squared plus 2n plus 1 times A. And we form a bipartite graph, G. And we assume that the loading capacity is given by C equal n squared times A. So we need the bidirectional transportation to meet these large need. So here is an example. So let's suppose we are given a set 11, 13, 24, 9, 16, and 23. And as you know, 11 plus 13 plus 24 is equal to 9 plus 16 plus 24. 23 is 48. So this is an example of a partition. Okay, and then we create 6 vertices and 2 special vertices and 2 special vertices having a large need. Then if and only if there is a partition, then we have such a transportation that meets all the needs. So here is a detailed proof, but it is complicated, so I will skip this proof. So we will consider the problem for our general graph. And we have 2 cases to consider. The first one is without constraint of loading capacity. This means that we don't have to consider bidirectional transportation. It's called double edges. And the other case is a constraint on there is a constraint on a loading capacity, and in this case we have to consider a bidirectional transportations. So let G be an input-weighted graph, and we can define a single round of transportation on G by choosing for each node U, the first one node V, which is target node V, among those adjacent to U. And we also have to choose amount of commodity to be sent from U to V and amount of commodity to be brought back from V to U. And we have equivalent transportation like this. For example, in here, we want to send S1 through SH units from U to V and bring back B1 through BH units of commodity from V to U. And if we reverse the edge, and also by extending those vectors, then the effect of the transportation on these two nodes are just the same. So these two transportation are just equivalent. So we consider no constraint on loading capacity. That's the easy case first. Let T be a single round of transportation on graph G. Then T defines the directed graph GD. The directed graph GD is called a realization of G. And such a graph GD has the following property, that each node is incident to at most one outgoing edges. So in other words, each node has so the outgoing degree of each node is at most 1. And then we have a lemma that GD consists of connected components, each of which contains at most 1 cycle. So the proof is as follows. Suppose GD contains 2 cycles in one component like this. Then there must be a path joining them like this. Then since every node on the cycle must have one outgoing edge, and the end edge of the path incident to the cycle must be directed toward the cycle like this. But it is impossible because both of them belong to the same path. So in this case, this node or this node has outgoing degree at least 2. What about the case of a component containing 1 cycle? Then in this case, we have 2 different directions of the cycle. One is clockwise and the other is counterclockwise. But for all other edges are directed uniquely, that is toward the cycle. And the component containing no cycle is easy because if we choose one node, say U, then all the edges are directed toward this node. But recall that we have equivalent transportation like this. So using this property, then we can since we have many nodes in a component containing no cycle, so we have many different ways of directing the edges. But we can choose one node and all the edges are directed toward this node. And we can, for any given direction, for any given ways of directing edges, we can reduce it to this unique directions. So we have unique realization in this case. So lemma 4 said that GD consists of the following connected components. One is component containing 1 cycle, C, and in this case we have 2 different directions. And in the other case is a component containing no cycle. In this case we have unique direction. And for each component we have at most 2 different ways of directing the edges, and thus we can find optimal single round of transportations that minimizes the largest need by solving linear program in polynomial times. That leads the following theorem. Assuming no constraints on the loading capacity, we can find for any weighted graph G consisting of components each having at most one cycle, a single round of transportation that minimizes the largest need in polynomial time. And we could extend that result as follows. Let G be a graph containing only a constant number of cycles. No matter how complex a graph G is, any realization GD keeps the property that each component has at most one cycle. So if we have polynomially many transformations of G into such a graph of the property, we can solve the problem in polynomial time. And that leads to the following theorem. Assuming no constraint on the loading capacity, for any given weighted graph G having only a constant number of cycles, we can find an optimal single round of transportations in polynomial time that minimize the largest need. So what about the case of finite loading capacity? That makes it complicated. Consider an easy case first where no cycle is contained in a given graph. Let G be a weighted graph consisting of trees. So that is, G is a forest. Different from the case of no constraint on loading capacity, we have to choose a possible location for bidirectional transportation to meet need larger than the loading capacity. Each component can contain at most one place for double edges, which causes some constraint on algorithms. We must separate a connected component into two parts so that each part contains at most one place for bidirectional transportations. So the problem is where to separate a tree. So we use dynamic programming again on the tree. So to implement dynamic programming, we define a level of nodes in the usual way from leaf to the root node. And root node is arbitrarily chosen. Okay, and we examine nodes in the increasing order of their levels. And suppose we have such a partition. Each component contains at most one place for double edges. So we cut here, and then we cut here. And this part is a bidirectional transportation. And in this large graph, in this large component, there is only one place for bidirectional transportation. Okay? Each connected component can contain at most one place for double edges or bidirectional transportations. And for a node U, T of U denote the tree rooted at U. If U is a leaf node, then TU is a tree of a single node U. For each node U in the increasing order of the levels, we compute two values, omega U of TU and omega C of TU. And U means the unconstrained case, and C means the constrained case, where bidirectional transportation are contained in some place. And for each leaf node U, we define omega U is the given vector, and omega C of TU is undefined. And for each internal node U, we compute an optimal solution, assuming that all nodes are joined by single edges. And so we solving all these linear programs, we have the initial value of omega U of TU. And for each internal node U, we compute an optimal solution, assuming that all nodes are joined by single edges, except for one place for double edges. And so we can enumerate all these patterns depending on where to put the bidirectional transportations. But we can enumerate all these patterns, and we can solve it all these linear programs in polynomial time, and choosing the best one as an initial value of omega c of Tu. So consider internal node U having V1 through Vk as its children. Assuming that omega U and omega c have been computed for each Vi. And we compute omega U of Tu, examining all combinations, cutting off the edges between U and Vi, or connecting them by a single edge using the value of T of U. And we can also compute omega c of Tu by examining all combinations, cutting off the edge between U and Vi, or connecting them by a single edge using values of omega U of Tu, and connecting them by a single edge using value omega c of Tvi, or connecting them by double edges using values of omega U of Tu. Then, skipping down all the details, we get the theorem. Given an instance of multi-commodity transportation problem on a forest, it is possible in polynomial time to determine whether there is a single round of transportation that meets all needs. And also, it is possible in polynomial time to determine the minimum need that we can achieve by a single round of transportation. And we can also extend the result as we did for the unconstrained case. So that is, given an instance of multi-commodity transportation problem on the graph containing only a constant number of cycles, it is possible in polynomial time to determine whether there is a single round of transportation that meets all needs. So here is our concluding remarks. We have proposed a new type of transportation problem allowing sending and bringing back operations. And unfortunately, the problem in general is NP-complete. And we obtained polynomial time algorithm for a graph containing only a constant number of cycles. And there are a lot of open problems. Among them, the first one is a polynomial time algorithm for determining the minimum need by 2 rounds or 3 rounds of transportations. Or we want to determine how many rounds of transportation are needed to meet all needs. And also, is there any polynomial time algorithm for a grid graph, which is most important, that is the most important problem for me. Thank you very much for your attention. ご清聴ありがとうございました。